Hi, everyone. Welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Vadum with Atlanta Functional Programming. Last week, we were discussing the Simplify case study that was provided to us inside the end of Chapter 9, particular chapter Section 9.6 of Paradigms of Artificial Intelligence Programming, Case Studies in Common Lisp. The specific ones that we ended up talking about mainly were the first three of the discussion points in the uh, chapter, well, in the case study specifically, when we're talking about memoization and compilation for a little bit. Although I will touch base on that even today in a little bit more discussion. But we ended the sort of episode last week or the session last week when we were talking about indexing specifically, just mainly because although I introduced a concept earlier last week when we were talking about just the final remaining pieces, I didn't really go through the example that was provided in the book. And I thought we might want to spend some time at least looking at the case study in guise of indexing, mainly because the first part of the section in the book, for those of you who have actually had a chance to take a look at it, there really wasn't much of an explanation about what indexing uh, really meant in terms of common Lisp, although it talked about it in the context of data structures in general. And rightfully, it pointed out that if you used lists as the universal data structure, which it is in Common Lisp for most of your uses, for small to medium-sized programs, you may end up, you know, being able to rapidly prototype and quickly develop a working feature for a particular program or even a sizable program with it. But unfortunately, it comes at the cost of a small, well, not small, a sizable performance degradation as the size of the lists end up growing larger and larger, mainly because, as many of you know, most linked lists and Lisp is not um, excluded from that list, um, are essentially pointers to the next item in the list, which means you end up having a linear time cost to actually look through every item in the list for particular types of searches, which in many cases could be very expensive, especially when you start looking at how the linked list is actually mapping to the physical memory and how ultimately the Lisp image pages out different types of memory in order to actually access particular items in the list, right? And the section specifically talked about and emphasized that it's very important to choose the right data structure and algorithm and in Lisp just as is important in any other language, mainly due to this pointer indirection. And it gave examples of different types of data structures that are already available at your fingertips, many of which we've covered in this stream. Some examples there are associative lists, property lists, which gives you the ability to look up by key, hash tables, which allows you to also look up by key based on a hash function, obviously, trees, which gives you a logarithmic time cost, as well as vectors, which give you a much quicker indexed access based on a numerical value that ends up getting converted into a pointer offset that Lisp, as well as other programming languages that implement vectors, use to actually go and access the particular item in that collection. Now, within the context of the simplified program, this means that we want to talk about how might we actually end up using it to look up rules. Now, if you recall, in our rule situation, and it looked like I opened up the wrong file here. We had um, a rule database that looks something like this, simplification rules, where these rules are set up to actually, obviously like many of our rules that we've written in other systems, whether it was ELIZA, GPS, or even student. You end up creating these rules. It does a quick linear lookup through each of the rules to find the rule that matches the correct pattern. And if it and it does it recursively, obviously, because of the infrastructure that we've written up until now, where was a recursive linear lookup through every item in the rules database. And once we find the item, we then use it to go and simplify the equation to something similar. But as we will soon see, we can actually go ahead and um, change this to actually simply index the simplification rules under the particular operator. Now, um, this is actually allowing us to avoid um, rules that could trivially be ruled out. Okay, this indexing scheme just actually allows us to index under each particular operator the set of rules that can be applied with that particular operator. So in Maxima, actually, in our previous thing, we've actually it was rewritten to actually allow us to write a simplify expression using rule-based translations. And let me show you what this will look like. Um, Let me by simply first commenting out our original one, as you see here. It just goes ahead and checks to see if it's an atom, and if it's an atom, it goes in and grabs an expression and simplify. And in simplify actual expression, we could recognize that this will actually go through a different set of conditionals um, using the rules that we've end up finding here. This rule-based translator, if you recall, it actually checks to see if the left-hand side of the rule that was constructed matches what's being passed in the expression. Then we can actually substitute by doing a sublist substitution in the action response to the response. We get the right-hand side of the actual expression, and then we can actually go in and further simplify it in the next recursive call as we go through it multiple times. So let's go ahead and comment this old version out for a second. And oops, sorry, we do that. There, sorry. And let's go ahead and here redefine our commented version here. And let's first load up, because I forgot to load this up for the stream, our PAIP. I think it's actually PAIP Lisp. No, 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 it is PAIP. I was right. Okay, and let's go ahead and set our package to it so that we can actually use the internal tools of that Norvig provides for us to actually go in and reload our Maxima. And again, this is a simplified version of Maxima, so keep that in mind. And we'll use this in just a minute. But let's go and see what the difference is between the two versions in a little bit more detail. Okay, so this is the one that we've that's the wait a second. Oh, this is not the one. Hold on, I have to actually bring in another version. Um, the index version has this one. Yeah, yeah, yeah. Okay, so first, what we need to do is we need to make a couple of adjustments here. One, in order for me to actually move this over, I'm going to have to actually first grab this guy here, and I will first go through what this simple version looks like once I actually, oops, sorry, let me close this window, and let's do this. Okay. Let's see here. Let me see if I can correct the um, no, this won't work. Let me see if I could do it this way. Well, just bear with me just for 1 second. I'm gonna have to. I was trying to see if I can write a quick adjustment here to this piece of code by just let me see if I could do this. QW, let's do this, and substitute space with nothing. Oh, my apologies. That's not what I wanted to do. 1 second. QW. Yes, space, global. There you go. Let's see if this actually can be used here at W. Ooh, it overcorrected unfortunately here. At W. Okay. Or by doing, let's see this. There we go. Unfortunately, one of the problems with this macro that I just generated, while it will simply work, it's just the cost of it running it is somewhat overcorrecting because of the fact that it can't recognize what is the end of a word, since different words have different lengths, right? So um, I could maybe do something more special, but I did not want to waste people's time to actually go and check that out. So basically this, and let me see if I can actually correct this guy very quickly. This percent done, and the one thing is simplified by function is actually a function name, and so we want this over here, and grab all these guys corrected. All right, this is coming together. Like this. So what this function is doing is it's grabbing basically the rules for a particular operation. Okay, as you see that each expression itself contains a an actual operator. Recall if you recall, and that operator ends up being used as an index into this hash table that we will soon create. That will then be used to search through. Okay, and this is essentially a way of pruning the database, um, well, the search space in order for us to actually go in and run the actual substitution algorithm, which will cause a significant speed up. Um, this, and then dollar done. This becomes now this. And in the action, this is the same typical action that we had before. All it's doing is grabbing the bindings for the particular response that we have, and it will go in and call the simplify function on the response. So, oh wait, my apologies. Let me go to that. And what this is doing here, and everybody has already probably seen this pattern enough from our previous episodes, which is we use sublist bindings response to actually do the substitution for us before we go and evaluate. Okay. And the rest of these conditions really are the same as before. If we actually go and look at the function here, although, one second, I think it's missing a, yeah, it's missing a parentheses here. Let me just go and double check this here. Valuable t. Yep, that's right. Okay, there we go. This is good. So we still have to define what rules for is and our actual database. Okay. Now we're gonna first define the database as a parameter. Let's go ahead and actually move this up to above 103, just so most folks can see this. And this is going to be our hash table. Our test function is going to be EQ. We're not going to use EQL or equal. Okay. Let me just quickly show you guys. This has a quick review here. So the main difference, again, if you see with our simplify expression here that we just commented out, okay, and this one, which is our new function, it's actually the second case there on how we're doing the lookup, okay, and we're constructing that right now. Instead of doing a linear search, we're essentially just doing a quick lookup using a hash table, which we're going to end up creating right now, and then two additional functions to actually go in and retrieve the information from the hash table. So given this hash table, we're going to define a function called mainop given the expression. And what this does is it's just going to grab the operator of the left-hand side of the expression that we're looking at. Okay, so for a given rule, we have this left-hand side and right-hand side. So we're going to grab the left-hand side of the rule. Okay, and let me just write this the way I would normally write this. Oh, sorry, not an expression. Let me go back to this. Okay. So we're going to grab the left-hand side of the rule, and then the operator that we're going to use, that's going to be what we're going to ultimately leverage to do the lookup, okay? Because that's what we need for the rule if you recall, okay? So the main piece here is there's two more functions now. Rules for is nothing more than a convenient function around get hash, which is what's used to actually go look up the hash inside of a hash table. Okay. I mean, sorry, the value for a given key inside of a hash table. So that's all rule 4 is. Okay. Actually, it's not rule 4, it's rules 4. My apologies. Okay. There we go. And let me just quickly unintern rule 4. Yeah, got it. All right. So we need two more functions now. Right now, the database currently is empty. Okay. We could technically run this, but nothing will happen. Um, so how do we actually go in and index all the rules? All right. So we're going to create a function called, the book creates this function called index rules. Okay. Given the rules that we are provided. And what it's going to do is just simply index each rule under um, the main operator of the rule of the left-hand side. The rule. Okay. The book had a simpler comment there, but it took me a little bit of a minute to actually go and see what he meant by left-hand side of the rule. And when I had to go and look up what main op meant, um, uh, I thought it would be a more convenient comment to actually add. All right. So let's say all rules is really what we're doing of a given rule, of each given rule, of each given rule. There we go. All right. First, we're gonna reset our hash when we do this. So this way we don't get repeated. If we call it twice on the same set of rules, we don't accidentally um, get duplicates. Okay. Even if there aren't duplicates, and most people know this, hashes collisions kind of could occur, and if you end up getting the multiple rules, it's going to just simply uh, go ahead and overwrite them. But this guarantees that we're always recomputing every time. Okay. With collisions, unfortunately, obviously, the way some hash tables might work is they might attach to a given database. I'm sorry, to a given key. I don't believe. I think maybe it might work like a multi-set, the hash table version of the common list. I haven't actually tried it. Collisions, I have to actually. It's very hard to actually create a situation where you hit a collision in the system implementation. Let me put it that way. All right. So once we have an empty hash table, we could then go through each rule, okay? And then what we'll do is literally we grab the hash, okay, value. And this is the pattern for if most people aren't familiar with this. Um, Get hash actually has a set f. It's a generalized expander. So it's just a set f on the get hash for any given value in the hash table. And what that does is this is equivalent to like, in Python you do like a um, open bracket key. This is the same pattern here. It's to grab the location of where we're going to ultimately um, write stuff into. And if it anything doesn't exist there, it'll just create the hash entry. And what this does is it uh, because we will have potentially multiple rules under the same main op, we want a list that is flattened and ultimately a concatenation of all the lists. So instead of a list of lists of lists, it'll just be a list of lists representing each rule. And I'll show you what this will look like once we actually call index all rules on simplification rules. Um, so the way we do this is we just call nconc. Nconc is the destructive concatenation operation in Common Lisp, and we call it on the main op the rule for the given entry, and we concatenate that with the new rule. Okay, and this is the index rules. So what does this look like? Well, let's call this here. First, let me require everything here. Requires maxima r. Shoot. Okay, 1 second. Sometimes this happens. It doesn't recognize the fact that it should actually reload the program. So set package PAIP requires maxima r. Okay, good. All right, so let's see how this looks. We call index rules on simplification rules. And if we look at rules 4 now, you'll see that there are 9 entries in here. But let's actually go and inspect this a little bit more. Well, the contents here, the left-hand side here is the key. That's the main op. Okay, each of these are symbols. And the right-hand side are essentially which expressions hit this situation. Okay. Now, when you run this, you're going to see some I'm going to just run a quick example on just some basic polynomials. Um, uh, but you'll see that the time at which it will actually go in and um, run this, on top of it being, if we actually memoize it, it will go down to a uh, kind of a 6.6, sorry, less than a second lookup for the simplification for most fairly complicated simplifiers, right? Um, and the way we do that is we could just run this on the expressions, but I don't think because we're not going to we can't necessarily time this originally in some cases for because I don't have necessarily the specific data that expressions that Dr. Norvig used to actually run these tests. Um, so, but I will point that from the data set he mentioned that this version that he wrote, which is nothing more than a simple replacement of the lookup from being a linear lookup to this use of this rules hash table that we created, um, drops it down significantly, which makes sense for anybody who looks up how hash tables work, and especially hash tables with memoization being used on the previous computation. So it's not just the fact that we do a quick hash table, which is a constant time lookup. We're also caching the result inside of the simplifier, so it doesn't have to look it up again, which is useful. Um, but my point is regardless, since I don't have the set, the performance of this is will be difficult to actually show. Uh, One comment I want to make about um, the compilation piece of this case study is that there are 2 rules that that we've already kind of covered when we were talking about compiler. Um, that I think actually, let me see. Do we have the compile rule version here? No, I have this for the different one. So if we go back to our exercise, hold on. Oh, so I have to go to my local projects because I've actually put the exercises under a different directory. Source main. I think this one is the one that has. No, this is not the one. Go to. Where was it? Oh, got it. Go to. It's in this one. Yeah, there we go. If we go back to this chapter 9 grammar compiler example, okay, and the simplifier is very much the same, okay. Uh, the simplification definition is going to do effectively the same thing that we saw here in the grammar compiler, okay. The only difference is the expression. So here, this compile rule, once we start building cases, the expression here is the lookup that we were talking about in the simplification database that we've constructed. It just goes and parses that to actually go in and grab the particular binding that it needs to go in and compile the rule into, and then it will leverage that to actually um, test the expression and then create the necessary transformation to simplify it. Okay. I don't really want to spend too much time on that specific one, just mainly because we kind of covered a very interesting version of this compile simplification rule before, with the grammar, and honestly, I think that was a particularly useful one to cover. Uh, this one is basically following in the case study, if I understood it correctly, the same sort of pattern of parsing the arguments, constructing the the expression builder to actually perform the simplification, and then when it compiles the actual expression, it actually goes in and uses a macro effectively to actually go in and construct the new simplified expression using those helper functions that we've generated up until now. Um, so the last part of this is something I kind of reviewed over the other sections already, and that's kind of a benchmark test that they've written. But again, given the fact that I didn't see any data in the Norvig set to actually go and see how he actually created these calls um, on the test data, and maybe it's because I didn't look too hard. Let me see. Since I have you all on, we may as well see maybe the meta. No. Yeah. So the test data isn't actually here for this piece. So you have to take some of his numbers within context of whatever test data he leveraged. These are the numbers that he ended up constructing. Um, and we can, kind of um, touch base on that moving on. Okay, so that's the end of chapter 9. Before I go on to chapter 10, and I'm only going to touch chapter 10 for like a minute, just because I really think that it it there are topics in there that require a little bit more deep dives, especially for those who haven't been following us along in previous conversations and just joined our for Paradigms of Artificial Intelligence Programming. But to give you a brief preview of what this topic is, Chapter 10 talks about um, what the author calls micro optimizations, um, where ultimately you find your bottlenecks and you use the techniques that Chapter 10 describes in order to gain additional performance advantages, and it'll make your programs run faster. Now, the techniques that he specifically calls out that I think we need to have some real discussion and see if we could try some of this stuff out. The first one we've kind of covered multiple times, although we've never actually dealt with it from a profiling and tracing perspective, and that is using type declarations. Okay, Common Lisp, contrary to popular belief, has type annotations and can statically type information. That's actually one of its ways to actually generate very efficient machine code, and you can leverage it in your code. And contrary, again, also to popular belief, uh, the static typing is leveraging the standard library as well. You can actually go look at it when you describe any of the standard library functions, usually even at the REPL. So to give an example of this, let's take uh, describe reduce. Okay, and if you go and look at the type information that's there, you can actually see the f type, the dynamic constant. It tells you that it's going to be a function. It has to be a function or the argument that needs to be passed in has to be a function or a symbol of a sequence. Okay. Um, it also tells you for each of the keyword arguments, the types they're kind of expecting as well. Um, some of it is declared when you run f type, and we will see this next time. But others are um, also can be provided in other ways. We've talked about types before in the past here, especially the type system and how you can actually create complex types. Some in not so much detail as others. We didn't go into type predicates that could be leveraged in this chapter. Goes through that a little bit, but type declarations we've kind of already kind of briefly introduced you all to, and we'll touch more about that next week. Um, a couple of other things just very quickly here before we end today's episode. Avoiding generic functions. This chapter is going to cover chapter 10. Avoiding very complex argument lists. This is also pretty standard. I have some opinions on this, even in general, in other programming languages, because this is kind of an anti-pattern in general that a lot of people tend to leverage, even in other languages. But there are three here that we've never really covered. We're introducing to you all and this is really a low level thing, but it can be used for creating very high performant code, and that is the compiler macro. Up until now, when we were talking about macros, we never really touched based on this. I may have introduced compiler macros in the context of one or two things before in the past related to, I think, squaring functions, just only to kind of show you one way of doing it and kind of give you the idea of what it was. We'll dive into what compiler macros are and how it is part of the Lisp compiler transformation system. And the last two is essentially stuff that most people should know when we were talking about indexing earlier, which is avoiding unnecessary consing. This goes back to also the last point, which is using the right data structure. If you're using something like Lisp's heterogeneous list has the universal data structure, you almost always will be consing at some point, just by definition, just because you're constructing a heterogeneous list. Okay. If you use other data structures that are provided in the standard library, or even third party libraries that could provide collections that are more correctly indexed, you will avoid that overhead and your code will naturally run faster and even in some cases compile to much more efficient machine code. But this is all stuff that we will be talking about next week. I want to have more of a focused discussion on it. I hope you all enjoy um, the rest of your Monday evening. And are there any final questions? at the Jitsi. All right. Well, um, enjoy your Monday evening, folks. Thanks for joining us. I'll see you guys next week.